All right. So let's hear what you got. So we'll just go around table by table, and you'll say one, and then we'll others can mark it off, and we'll see who goes longest. All right, this table. What's something you have?
Bike.
Bike. Okay. Yeah. If it's an aluminum or steel bike, probably has welds on it.
Shower head.
Shower head. Not sure that there are welds in a shower head.
Actually, I put it on the list last night for it, and I like went up to it.
Oh, you got it.
I went up to it and looked at it, and it was like, heavy duty shower. I thought.
Maybe like the plumbing that goes to the shower head?
No, plumbing is soldered. So the difference between soldering and welding is that in soldering, the base metal doesn't melt. Only the filler metal melts. The base metal stays the same. In welding, both the base and the filler melt and become one together. If you looked at your shower head and it's welded, I've never seen one, but I'll take your word for it. All right, this table.
Table.
The table, what part of the table?
The feet.
The feet.
Like where the.
Are they?
Looks like it.
There's some pieces there that are tacked on.
I think so.
The top between like the actual like base plate and the,
Okay.
and the pole.
Well, okay, the base plate underneath at the top of the pole. All right. And it could be that the end caps on the tubes are as well. All right, good. Tables.
These chairs.
These chairs, yes, they have little welds at the back corners to weld the wire together.
The tailpipe of my car.
The tailpipe of your car, yes. Infuriatingly, exhaust systems are welded so that you have to weld them and you can't just unbolt them. All right, this table.
Toaster.
Toaster. The little grate thingies. They probably are. They might be brazed, but we'll say that they're welded. That's good. That's a great idea.
You said a braised?
Braised. So in brazing is like high temperature soldering. So again, the base metal doesn't melt, only the filler metal does, but the filler metal in brazing is a high temperature melting material rather than solder, which is very low temperature melting. So it's a structure.
Might be braised.
It might be, yeah, I don't know. Brazing is structural, whereas soldering is only for sealing things off or electrical conductivity. It's not very structural. All right.
Railings.
The railing, yeah, railings are soldered, and if you go and you start welding, you will be frustrated very quickly with how hard welding is, and then you'll start looking at things like railings, you go, oh, everybody else is a crappy welder too. That's okay, I don't feel so bad anymore. Some of them are really bad. When they, let's see, what railing was it? Oh, that was at the last place that I worked. They spent all this money on this new building, and then they had to come in and have somebody spend a week sanding down all the welds because they were a little too sharp, and some safety person decided that they were not good enough. So, well, okay. This table, what do you got?
Sewer pipe flanges.
Sewer pipe flanges. I don't know.
You did that this morning?
Yeah, so,
I bet the old ones are. The new ones are like composites now.
yeah, the new ones are composites.
How old is your
The
dog?
septic system in our house is not correct.
Okay.
I think the old ones are soldered
And
though.
that's why I had to look at it this
I
morning.
don't know. Typically, they would be soldered rather than welded, just because it's hard to weld something that big and get the heat into it. But it could be true. Yeah, especially around the flange. Yep.
Bus stop.
The bus stop,
The bus stop.
like the structure at the bus stop, or the.
That's totally
The part that.
All right.
The sign and the
ran off you and you're.
Okay. All right, I'll take that. Yes. Back table.
Stool.
Which stools?
The ones at our house.
Well,
Let's take a trip.
Real, hard for me to argue that.
The chassis of my car?
Yes, there are tons of welds in a car chassis. All right.
Street signs.
Street signs, what part?
The part that connects metal pieces together.
Mostly they're bolted.
But there are some on the sides. I was thinking of that.
Of what?
Street, like the part of signs, like this.
Oh, like the sign parts, the pole part?
Yeah.
The
Like,
street,
wait, like a
street
street
lights
light?
or street signs?
The stop sign.
You know what? Just for you girls, street lights.
Okay, so street lights I'll go with. Street signs are generally only welded if they got lopped off by a car and they had to stick them back together.
So it can happen.
It can happen, but it's not common, yes.
Boats.
Boats.
You interested in the
What
boat?
kind of boats?
Down by the dock, you know.
The water.
Aluminum boats have sick welds.
Yes, aluminum boats have sick welds, and if you want to see some really good welding, going down to All American Marine and watching those folks build aluminum fast ferries, they have some awesome aluminum welders. Yeah.
Cooking pan?
Cooking pan. What kind of cooking pan?
We had like a stainless steel one. Had like a thing. Two metal. Yes.
Where the metal goes on?
Yes.
Did it have rivets?
Did it have rivets? I didn't see any. I didn't see any screws or anything. It was just attached, so I assumed it was welded.
Interesting. Yeah, it could be. Most of the time they're riveted on, but it could have been, yeah.
We need to do like show and tell.
It's just more expensive to do it that way because it's hard to keep it all square. And it requires somebody with skills, whereas the riveting requires somebody without skills. All right, back table.
There's a monster weld that holds up the triangular sculpture.
Yes,
Oh,
there is.
yeah.
In that upper corner, there is a really big,
Four-pass weld that's
yeah,
pretty sick.
yeah, somebody spent a lot of time on that. All right, back table.
Towel rack at the house.
I'm starting to doubt their house. It's okay.
We said the gas tank of my car? It's aluminum.
Okay, we're gonna get to every part of your car. Excellent. This is gonna be a long time. Oven rack. You folks are just in the great business today. Yes, oven rack. Good.
Car bumper. Like a custom off-roading one.
Oh yes, a custom off-roading bumper. Yeah. Okay. Right. Next table.
Dang it.
Oh yes, yeah. When they're all stuck together and you can't get it far enough away from your table to kick back and lean back. Yeah.
I don't know what it is, but at home Wes just has like a bar with like a screw welded into it. Just, I think you're just testing his weld kit.
All right, now we're to random art. Okay, excellent. Yes. At their house.
My bed frame.
Okay. Yep. Can be.
I can take a photo.
The suspension of my car?
I would say that the suspension of your car is a step too far, probably.
Okay.
Because you have the frame already. You already did that.
Yeah.
So all this, the members of the suspension past that point are generally bolted together.
Does chassis include the axles?
The steering.
Wait, I had. Oh, like dumpster?
A dumpster, yeah, dumpsters have welds. We used dumpsters to store, I don't know, 80,000 pounds of molten salt, and we found out that the welds in the dumpsters were not that good. They started leaking molten salt, but anyway.
Wait, you just throw out molten salt?
Well, it's 8, yeah, it was 1,200 degrees Fahrenheit, so it stays molten for quite a while.
Okay.
Yeah, it's hot. All right, yes.
The big chair.
The big chair in front of Old Main.
The big chair in front of Old Main, yes. Does anybody know why the bear had to leave?
I don't
It
know.
was-
It
it
was
was inappropriate.
People in the
I know, but at a
Originally
time,
it was supposed to be there. Yeah.
I know,
Originally,
but-
the artist didn't want
I
it
don't
to be
think
there.
Do you think he gets entries?
Or
when,
people.
when we're in the budget situation that we're in,
Yeah.
and they
Yeah.
spend that much money to move a sculpture, there's gotta be a backstory.
Have you
There's-
seen it?
I think people were complaining about
it's
it.
odd, but there's gotta be a backstory about the artist did something wrong or appropriation or something.
Somebody on the board was like,
I read the
Yeah,
post.
and-
you can't have as much and such fire on the front lawn.
You know the little people.
Could be.
on the
Yes,
artist?
do you have another?
The artist that did
My
those
roommate's
also
fish tanks,
did it where he
which is,
killed an
cut and
alive, like he killed
Do
an
do you keep it at Abby and Mia's house?
No.
All right, back table. Do you have another one?
Yes.
Oh, yeah.
Were they tired?
Maybe we have.
Oh yeah, Wes also, I think last night just had like a plate that he was testing welding on.
Okay, at
That's a
some
lot of
point,
fun,
we're
dude.
gonna have to get to things, not just, test subjects, yes.
Row machine?
Okay, all right.
My scooter,
At my house.
Scooter,
where the
okay.
handlebars meet that thing.
Yeah.
Good stuff.
Yeah.
Boss handrails, yes. Okay, good. That's enough of that.
Yeah, maybe I had like
That was last year, just so you know. This is this year. You did great.
What was last year? Go back.
Go back.
Oh.
Oh, yeah, we
Ours were cooler.
Ours are.
Oh, these are made.
Wait, which one's
Wait,
Mari?
Last year.
How did,
NID.
how did that person
Oh,
use
and
that
I-
weird like
Where's Mari?
triangle?
Mari Wu over there with the cat ears.
How did they do it?
So like bottom, like
Yeah.
four from the right, how they get it to spin?
Oh, look here, that's magic.
Is that not against the rules?
It actually worked. It was surprising. Yeah, it did work.
Bottom.
Because it was exactly the right size to fit the bearing. Yeah. Yeah.
Brooks always corrects me.
So, and we had a couple in other years, I'm not, oh yeah, we had this one right here also, which just grabbed the bearing. It was pretty tenuous, it was hard to machine, anyway.
Which one? Breeze?
No.
Oh.
This one, because it's, it doesn't have a full bearing containment, so,
You
yes.
see the one that's like center left? Did it just not cut out all the way?
This one?
Yeah.
Yeah, when I took this picture, I still hadn't been able to get the rest of the material off of
Did you
the fish.
get it off eventually?
I did,
Oh,
yes.
good.
That one was
So sick.
super
Which
hard to
one? Oh,
machine.
Braverman?
The birds are.
Oh, yeah, that one's cool.
That was Enrique's.
Braverman?
Braverman?
Eli's.
Owen Eli's, and then he lost him.
All right, lots of welding. Why is welding so prevalent? Why is so much welding done? Ah!
What happened?
I don't know. Things.
Connects metal pieces.
Your home screen is in here.
There we go.
Aw.
Why is welding so prevalent? Yeah.
Because there are many options, because we frequently need to stick two pieces of metal together, and because there are a variety of different styles, and with different people with different levels of skill and different, like, needs of quality. That was a weird way to phrase that. but,
Okay.
like,
Yep.
exists.
All right. So lots of ways to do it, and lots of, but why not screw them together or something else? Yeah.
It's pretty strong.
It can be very strong in comparison with the others. Yeah. Okay. It adds a lot of weight when you weld. However, if you bolt things together, there's always an overlap. And so in an area, you're doubling up the amount of material you have for no structural reason other than that's how bolts work. And so that also adds weight. It is surprising how much weight welding adds to a structure. If you actually go through and weld a big structure, it's a pretty considerable amount, and it's easy to way overdo it and to just take the weight of something that you were hoping was going to be really light and just put together with small welds. It's easy to add a bunch of material to it that you didn't intend to. Most, it's crazy, I don't know what's going on. So yeah, most people haven't seen submerged arc welding, and so I thought I would show that. We'll see if this actually runs as a video, or if it's just a picture. It's wild.
I think the link is good.
If we click the link though, we probably have to watch commercials.
Okay. It's okay. I'm used to it now.
Alright. Alright, so, it won't maximize for whatever reason. So this is welding a pipe, and you'll see that they set it up here to weld the pipe. It's dumping the kitty litter type material around, which keeps oxidation from happening on the material. You'll notice you can't see anything that's going on. So, wow, hope it's working right down there, or else you just wasted a lot of money of pipe and of weld material. Very often they will have another thing that's right behind this that's sucking up the kitty litter after the melt has cooled enough that it's not going to oxidize. This one, they appear to just be dumping it on the ground. There is a filler metal that's going in. You'll notice that it's cranking. That's a lot of filler metal that is being used there. And then, in a minute, notice that it is 30 volts. They're keeping it 69, I don't know, 69, I don't know what that other statement is, but 30 volts, so they're keeping it under 50 volts. And then, if it will let me, yeah. So it's a pretty awesome looking weld at the end of that. Surprising what that is. It is sturdy looking. Now, a weird thing about that is that you have to be able to rotate the whole pipe to get it to work, because that only works on a horizontal surface, and it does not work on a vertical surface. And so, anyway, that's a challenge, because you can do that on, when you just have two pipe sections, you can't rotate a mile long pipe. So you have to figure out what you're gonna do then. It's just angry. That's all there is to it.
Whoa. Yeah, look at that. Whoa. Aw.
All right. I mean, let's see here. Something is awry.
I'm starting to think something might be alright.
This seems like a thing. Okay, things that can go wrong when you are welding. You will have a leg length specified, much like a fillet or like a chamfer. Welds are specified by the length of the leg, not by the length of the hypotenuse. This is a little inconvenient because you can't measure the length of the leg once the weld is there, because the material, the weld is in the way. So this is just the way that they're called out, and it's because of the strength of the weld comes from the amount of leg length. So things that you can do, you can over weld where you put too much weld metal on there. That can have a bad function because of the heat affected zone, so you will damage too much of the material around it. So when we heat it up really hot, the grains all grow there, we lose all the strength in the material, and we have too much ductility. And so you may have a very strong weld, but material all around the weld, we can lose that. If you happen to have excess weld material and it's bulging up like this, it leaves these sharp little notches on the ends. Those sharp little notches are nearly impossible to get paint into, but the water will pool in those, and then it will cause very rapid rusting, because it is down there in that heat affected zone that already has poor properties. And so that's a bad thing too. Anyway, lots of other ways to screw up welds. Bridging is really easy to do when you don't get far enough down into the corner, and it can easily look like it's a good weld, and it's hard to tell that it bridged in the back. But This happens a lot with beginning welding when people aren't willing to get their head down there and look really carefully where they're welding. It's also easy to not fill in all the way if you have a groove that you're supposed to fill in. And so this is something that you can go back and repair. The incomplete fusion is hard to repair without grinding everything all the way out. So when we look at a weld, we have this area called the HAZ, the heat affected zone. And the heat affected zone is really critical to a weld because it's all uncontrolled. Actually, everything in the weld is not very well controlled. So we don't know the properties of the material that are in the weld, and we especially don't know the property of the materials that are surrounding the weld. But the thing that we do know is that this area around the weld is going to be weaker than the base material. And so that means if you are doing something where you're welding it together, very often the material ends up having to be thicker than you would like it to be in the end because of this heat affected zone. You can get somewhat rid of the heat affected zone if you can take the entire structure and take it up to the austenitic zone and then bring it down and do a treatment, heat treatment on the whole structure. But that's very hard to do because the materials around the weld will react differently to the weld because they have different thicknesses. So it's challenging to do that. And also, often structures are big enough you can't do that very easily. So we often have to live with whatever the material properties are of this heat affected zone, and that will be the thing that controls the strength of our final product. Things that can really affect the heat affected zone is the abilities of the welder. If you have a good welder, they can weld quickly and not way overheat the material. And if you have a welder like me, then I can add a whole lot of extra heat to the material and cause a bunch of damage around the weld. And so when you have something that is critical, you end up using certified welders. So when I worked on the molten salt project, we had pipes that were 8 inches in diameter. They ran at 1200 degrees Fahrenheit, 600 PSI, and 600 gallons a minute. So there was a bunch of molten salt flowing through these. If we had one of those leak, it's an incredible safety risk to people who are standing anywhere nearby. And it's also very expensive because the molten salt was hundreds of thousands of dollars to fill the entire system with molten salt. So what you end up doing is we had, because it's a pressure vessel, we paid for 3 guys to sit in a room for 3 months welding coupons and testing them. And they had to do that until they had 100% of the coupons pass the test. And then that certified them to weld this certain material combination that we had. And then they came out on site and they did all of the welding in tents where they were protected from the environment. And then every 5th weld got full radiography where they used x-rays to look for any cracks that were in it. Every weld they coated with dye to see if there were any cracks that showed up. You put dye in it and then you use an ultraviolet light to look at it. And then about every, can't remember if it was every 20th or every 50th weld, they actually made the weld, cut it out of the pipe, and then sent it away and did destructive testing on it to see if it was good enough. So this is a huge expense when you're doing something that is a life safety issue. For us to pay for those people to spend 3 months just developing the skills. I mean, these were qualified welders, but they had to qualify on our specific materials, and then they spend 2 months on site welding the parts together, and the cost of doing all of that radiography and sending all those off is really high. Yeah.
So they're welding the pipes that your molten salt is going through, so that big structure you showed us?
Yeah. Yeah, with the molten salt going through it, and then the structure expands more than a foot, so there's a lot of stress on the pipes. Yeah.
Out of curiosity, how much do those welders get paid for a job like that?
I don't know. These were pretty good. These guys got paid pretty well because they were certified for that pressure and that stainless steel. It's not a bad gig. if you're a good welder, yeah.
What kind of welding were they doing? Were they,
I think it was TIG. I think it ended up being TIG. It was stainless steel.
Yeah.
We didn't actually get to specify the type of weld. There was an engineering company that was responsible for that. Okay, so all kinds of grain growth that's uncontrolled. We have no idea what the material composition is, because if you think of what's happening in this weld, we have material A and material B. Those are the base materials being put together. Maybe we have a backer plate. Maybe it's the same material, maybe it's different. And then we have this filler metal going in. So what is the composition of that material in the weld? Well, it's really hard to know, really hard to know. So we have to choose what its properties are, and we choose its properties by choosing what material we're putting in as the filler metal. So we almost always make the filler metal have a higher strength than the base metals. Almost always. The one case in which and so that's called overmatched. So if we are putting in a higher strength filler metal, then that's an overmatched weld. We can match a weld where we put in the same strength material as the base materials, but the problem is, because this is uncontrolled cooling, even though it was the same strength when it went in, it isn't anymore. Because it cooled at some random rate. The one place where we undermatch things is when we have really brittle materials. If A and B in this are really brittle materials, if we overmatched the weld and then it shrinks, when it shrinks, it's going to put incredible tension on the two pieces of base material. And if they're brittle, it will just break loose from the base material. So when we have really brittle materials, then we undermatch, and as the weld cools, then it will stretch to fill that rather than breaking the two pieces of material on the sides. The way that you do this is you look up the material that your base material is, and it will tell you what kind of filler metal to use. And so there are charts of this from the companies that supply filler metals. So you just go and find what your base material is to figure out what you should be using as a filler metal. Yeah, that's fine. When you do this, you get all kinds of residual stresses going on because you weld along the seam and then it cools. When it cools, it will shrink. That's putting, it's pulling on all the material around it, so it's in tension. The material on each side of it is in compression because it's the weld is trying to make it shorter, so it's trying to compress everything on the side. And what this will do is cause your part to change shapes. And it will either bow or potato chip or lean or do something to change shapes. When we did the 3D printing with the welding, we would draw one line of weld on a 1/2 inch thick plate of stainless steel, and it would potato chip more than 1/8 of an inch for just a piece that was about 8 inches by 8 inches. So it would do more than 1/8 of an inch of potato chipping, and there was nothing we could do to bring it back. We tried doing a little bit on the front and flip it over and do a lot on the back. Didn't matter. If you had touched the front, it would potato chip. So to get around this, we often tack weld. So you go in and you put little tacks in where you're putting in as little heat as you can to set the shape of the structure beforehand, and then you go back and fill in the complete weld. You can try to clamp the thing in place. That doesn't usually help very much. So generally what we will do is weld it and then afterwards try to anneal it to get some of the residual stress out. So we'll take it to a middle temperature, anneal it, and take the stress out if we can. That's hard to do. There is something really cool that you can do with this though. Oh, no, I took that out. Never mind, there's nothing really cool that you can do with this. So the really cool thing that you can do with this is on the old hard drives, so the hard drives where the disk actually turns in them, so not the SSDs, the reader head in those disk drives has to fly off the surface of the disk as the disk spins. And it has to be close enough to read little tiny magnetic signals, but it cannot touch the disk or it's done. And so the way that you do that is you take a little tiny piece of silicon and you just hit it on the back with a laser, and when you do that, it will bend up just a little bit and it creates a wing on the bottom side. And so when the disk is spinning underneath, there's a layer of air that sticks to things when they move, and that layer of air will travel underneath this wing and cause the wing to have just enough lift to support that read head in it. I think it's 4 nanometers off the surface, something like that. It's incredibly small, but they just do it with physics tricks, which is pretty cool. All right, 5-minute break. Yeah, so 2 till 10, 11, some hour.
The QR code. Gingerbread.
Why do I even ask you
It's a Google. I'm like, what was the actual question? I just got
See, it has a bunch of words for it.
I know, I'm looking at your PowerPoint. I forgot my glasses, so your PowerPoint's on here. I'm looking at it.
Oh, that's why you're wondering. Oh, it's a flyer for a gingerbread house building competition.
Which you should join, so you can lose.
It's sweet.
Whoa, Gil, okay. Are you like notoriously good at gingerbread house making? Or do you have someone you're rooting for? Like, do you have a...
No, Robert and I we're doing this and we're gonna win.
Right? Like,
Is it your pro welding skills?
I cannot reveal
Oh, I'm sorry.
why we're gonna win.
Alright, well, when I join,
Maybe it's just arrogance and confidence, something like that.
that does sound more like you.
On the feet.
I don't think it'll take long.
I really
I just put the frosting and also the marketing. It's like a little bit too way financially. Gingerbread house.
You were writing what?
I was writing PowerPoints, like, we were like, we shaped it as presented over the front.
No invite?
And
It's like a public invite. What do you mean? Literally anyone can join. AJ, do you want to go to gingerbread?
Okay.
Yeah,
I did. Gil's gonna be really competitive though.
No.
You know, he just scared me from joining, to be honest.
I like that there's like a QR code you scan and you can answer no.
That's so funny.
You want to do this? Nope, but I felt peer pressure to scan this QR code.
I like it. It's kind of like an out. Everyone's like, scan it, scan it. What day is it? Next Monday? Okay, I'll come.
Yay.
Alright, I'll bite.
What?
You'll do what?
You work.
You guys should watch my YouTube channel. I might get the red out of your YouTube. My name? Is it Richie Lemon? Well, it's also, I think it shows up every time for Alexa. Yeah.
So I got
Like, twice a year.
Richie made lemonade.
That's me. I hate to break it to you, but I'm actually famous recognition in disguise. Yeah. T-Made is crazy. Dude, they put ice spice in it.
Yeah, like a whole bunch of different fonts.
I don't know.
Oh, you know that.
I do know that because
We love ice spice.
All right, here we go.
It's like they put ice spice in Fortnite.
So, wanted to talk about some of the other ways that we weld things together. And spot welding is very common, but then some of the ones that are a little bit less common that you may not have seen before. So spot welding is pretty cool because you have an electrode above, you have an electrode below, or they can be on the sides, but electrodes on the outside, you have two pieces of material, and it applies a high frequency electrical oscillation between those two with some pressure on them. And when it does that, the two pieces weld together. Question is why? Why do the two pieces weld together and the electrode doesn't weld to the side? Well, that occasionally happens. But mostly the two pieces weld together. And it's, again, physics being cool, or maybe chemistry, I don't know. At this level, who can tell? So what happens is right here at the interface is the surface that's oxidized. And so that has the highest electrical resistivity. The electrodes are made of copper so that they have very low resistivity, and they tend to have a surface that somewhat bites into the oxidized layer on the outside so that it will get good conductivity. And so when you flow this electricity, especially with a high frequency on it, what happens is this surface at the interface will heat up because it has the highest resistivity, and it will heat up enough that it will weld those two together. So this is a super easy way to weld things, and it's great for lots of things. It requires you to have the materials overlapping, so you have some weight penalty that you pay for this. Also, it is only welded at the little spot that you did. And so when they do welding on a car, there are there are tens of thousands of spot welds on a car because they do all these welds all along. Now there is a way that you can actually, so a car contains 2,000 to 5,000 spot welds. The way that you test them is you pull them apart, and it looks like a tear test if you were checking an adhesive material. And it's essentially the same thing, and you are expecting the material to fail in the heat affected zone. If the material fails in the welds, then you have to go back and redo all the welds because your welds are junk. There is a cool thing, just a second, that you can do where you can put two rollers on it, and then it pulses on and off, and it essentially makes overlapping spot welds, so you can create a seam weld along a line, but it's just a lot of spot welds lined up together. Yeah?
Why is AC use spot welding instead of DC?
But there is something with the high frequency. If we went through electrical calculations, it makes the resistance resistorier somehow, so that you get higher heat from it. Yeah, I'm not 100% sure. But when you hear a spot welder, let's listen to a spot welder actually. So this is Sal, and the Smart Welder 2000. You'll notice that the machine is the Smart Welder, and maybe Sal is not.
Hi, I'm John, and you're here at Rudy's Auto Body. Today we're going to talk about welding on replacement panels, auto body repair panels. We're here with Sal, our body tech, as well as our car liner CR2 12,000. This isn't just your ordinary welder. This is what is referred to in the industry as a smart welder. This welder will determine the type of steel that's being welded, as well as the gauge or thickness of the steel, and adjust accordingly so that you get a proper weld every time. We're going to go ahead and do a couple demonstrations for you.
So listen to the high frequency when Sal makes this magic happen.
What you just saw is Sal activating the welder, and the welder itself will determine, again, the type of steel, the thickness of steel.
If you have any seam welding needs, Rudy's Auto Body is the place to go.
And produce a proper weld.
The thing is that you can tell that Sal is happy to work there, right? He looked like he loves his job. All right.
Especially the supervisor.
Yeah, he really respects John in every way. Another really cool thing that you can do, it's very hard to weld materials together that have vastly different melting points. Because if you try to weld them and the weld, as the metal cools in the weld, some of it will solidify out long before the other solidifies out. And so the metals just won't stick together. So instead, you can do something called forge welding. So remember, we need pressure and we need a clean surface. And so you can take two rolls and you roll them together, and at the same time you're squashing three pieces of material. So you have two surface coats and you have a middle. And the material in the middle is getting flatter and longer, and so it is rubbing against the outer material really hard, which causes a clean surface in there and then an immense amount of pressure. So the really neat thing about this is you can weld materials that have just wildly different melting temperatures. So if you have an all-clad pan that has stainless steel on the outside so that foods don't react with it, but stainless steel is a terrible conductor of heat, then they put a copper layer in the middle to conduct the heat so that your pan won't burn things, and that's done by this process. So they forge weld the materials together and then bend it to shape and roll the edge over so you can't see the copper that's inside, but it is there, and that's how they do it. So pretty sweet technology. That is why they're so darn heavy. That's right.
That always perplexes me.
Another really cool way that you can weld things together is just friction. So you just take something that's spinning and you press it against something that's not spinning, and it will generate a tremendous amount of heat. It will rub all the oxides off there, and then it will finish at the end. So here we go. This is a process. You'll see over on the left is the side that's spinning. It's like a lathe. At some point, the motor disconnects from this, and you can see that it has a huge flywheel on it to keep it spinning. The piece on the right is stationary, and yeah, pretty neat if this is what you need to do.
How does inertia welding work? Basically, by forcing together pieces to be joined in such a way that rotary motion and pressure are converted into heat, which literally bonds the pieces into one part. Two pieces to be joined are aligned in an inertia welding machine. One piece is held stationary, the other is rotated rapidly on a spindle chuck attached to a flywheel. When the flywheel reaches a predetermined speed, it is disengaged and the freewheeling piece is forced against the stationary piece. Friction between the parts heats the budding surfaces to forging temperature. Just before rotation ceases, the two pieces bond automatically. When the flywheel stops, the weld is complete.
makes you that happy, it must be a good process. Let me out.
Thermite welding.
Yes,
So cool.
thermite welding is cool. Oh, great.
America.
How would you learn about friction stir welding?
We will learn about friction stir welding.
Please
Do
do.
not worry.
It's environmentally friendly?
Okay, so friction stir welding is kind of the same thing, except that instead of welding the spinning thing together, we're using the spinning thing to stir metal from two different pieces together. So this is a really cool process because when you do friction stir welding, you're not overlapping two pieces of material. We're not doubling anywhere. And in fact, we're not even adding any material to this. There is no filler metal. So what you do is you take something that looks like a dowel pin, you butt two pieces of material together, you spin that dowel pin up to speed and shove it through the two pieces of material and just follow along the edge, and it stirs the metal together from the two pieces. So pretty amazing that you can do this. It's a great thing for something that you need to keep lightweight, like an airplane or a rocket, something like that. Yeah.
So on an exam, would you want us to know the difference between each of these types of welding?
I would want to, yeah, kind of the differences between them, or why you might choose one. Why would you choose to do friction stir welding?
Rather than just normal friction?
Yeah.
Okay.
And the reason is, I don't know why anybody does friction welding. Because frankly, I mean, when do you get a point where you're like, dang, I cut this bar into two, now I need to stick it back together. Just buy a longer bar. I mean, really. You could do it if you needed to take one shaped thing and stick it to something else, but it seems like a really niche operation. Anyway, this one seems pretty cool. So there was a company in Albuquerque that made airplanes. They still make airplanes. They've, anyway, called Eclipse. And they decided to make small business jets, and their goal was to have a small business jet that costs less than $1 million. And the way that they were going to do it was they were going to use friction stir welding for the entire fuselage of the airplane. So when you think of an airplane is a pressure vessel, right? You take it up really high into the atmosphere where you have to pressurize the inside so that people can keep breathing. And if you have a plane that's created by traditional methods, you're riveting a faceplate to a frame, and you're riveting it hard enough with goo in the middle so that it will create a pressure vessel. But that's not a very good way to create a pressure vessel. It would be a lot nicer if we could just use a single piece of metal to do it. Well, it's too big to use a single piece of metal, but you can create a single piece of metal by taking big circular sections and then friction stir welding them together. And you can end up with the fuselage of the airplane essentially being a single piece. So that's really cool. Company went out of business. Why did it go out of business? Did it have anything to do with friction stir welding? No. Friction stir welding was awesome, and actually they're back in business, still making jets this way. It's funny the way that they went out of business. There were two poor decisions made. The first was they wanted to use a low-cost jet engine because that's very expensive. And so they found a low-cost jet engine that actually they've made hundreds of thousands of these low-cost jet engines. The downside is that they're used on cruise missiles, which only have to operate for 2 hours, and then you're not getting the engine back, so you really don't care if it runs again. So it's not really a good engine for durability because, so anyway, they had to change engines. That bumped them up to $1.5 million minimum price, and so that was a problem. But the big thing that sunk the company the first time was that the jet did not have enough room for golf clubs. And what people do with a business jet is you get in the jet, you fly somewhere and pick up a customer, you fly somewhere fancy and you go play golf, conduct some business deal on the golf course, and then you fly them back, drop them in their golf clubs off. And they didn't have room for golf clubs, so people wouldn't buy the jet.
How small was this? Golf clubs aren't that big.
Well, but planes are really small. If you get in a plane, they're really tight. Like a business plane in the sub-$1 million category, it's a really tight plane. So
Do you know what
you're friendly in there.
if they ever produced it?
Sorry?
Do you know what the model was if they ever produced it?
So they make the Eclipse 500 now, which is big enough to have golf clubs. It was like the Eclipse 250 or 300, something like that. They made some of them, not a lot of people bought them. I mean, business people who wanted a cheap plane and don't like golf. So I'm all for that. This is how friction stir welding works.
One of the challenges to more widespread use of aluminum in automobile construction is joining. Friction stir welding is a process that allows us to join two materials together without ever melting them. We use a tool which is rotated and plunged into the interface of two abutting plates and then stirred down that interface in order to locally forge the materials together. Traditionally, the automotive industry has considered friction stir welding too slow of a process to put into high volume manufacturing. Here at P&L, we increased the friction stir welding process from less than 1 meter a minute to 3 meters a minute and beyond, which enables that process to be used now for high volume automotive manufacturing. The unique aspect of this partnership is that we brought together the material manufacturer Alcoa, the automotive supplier TWB Company, and the automotive OEM General Motors. By working directly with Taylor Welded Blank Company, they were able to put in their facilities in Monroe, Michigan, a dedicated friction stir welding machine that's capable of producing up to 250,000 blanks a year. This is a first for the automotive industry. One of the surprising things that we found was that as we increased the speed, the performance of the materials increased as well. Whether we're speaking of surface quality or formability, higher speed made a better joint. High-speed friction stir welding is enabling more widespread use of aluminum alloys throughout the automotive industry.
Two other things that I wanted to talk about that are not soldering, just to be clear about what they are not welding. The first is soldering. Soldering is where you use a low melting temperature material to join two pieces of material together. The two base materials do not melt in soldering, and this is primarily done for electrical conductivity or for sealing things like water pipes. Beyond that, it's not very useful because it's not structurally a good way to support things. The other is brazing. In brazing, again, the two pieces of material that you're joining are not melted, but this time we use a medium melting temperature material, so it is a structural joint. This has to be done under high pressure, and the temperatures are high enough that you have to do this in a vacuum furnace so that you can control the environment. Otherwise, you would get lots of oxidation in the braze, and it would not be a good structural joint. So those are two other things that folks often get confused with welding, and they are different. Brazing is pretty cool. There are lots of times when brazing something together is a better way to do it. So what we do is you take something and you assemble it, and if you have a really tight joint between the two pieces, you put braze material around the outside, you heat it up, and the braze will actually wick up and through the entire joint. So it will seal together a lot more than you can with a weld. Because if you're doing a weld, you can only put it at the outside edge. You can't weld all the way through the length of a joint, especially if it's got kind of a crazy shape to it. So the place that a lot of this is used is if you've been over in AMSEC using things over there, or in vacuum furnaces, stuff like that. Very often, those more complex shapes that are put together, the insides of a scanning electron microscope are almost always brazed together, because it's a great way to join two things together, but it has to be small enough to fit in a vacuum oven. So it's not very good for scale, and it's not very good for speed, because you have to put it in an oven, suck down the atmosphere, maybe refill it with some inert gas, and then do the heated up to a high enough temperature and then cool it down in a controlled way. So it's good for scientific equipment and other things that cost money. A little bit about weld safety. So welding is something that is very accessible. It's easy and inexpensive to buy a welder, and you can just plug it into your wall outlet and go after it and start welding things, and it's super fun. But there are some things you have to be careful about. One of them primarily is fire. When you are welding, it creates sparks, and people often don't realize that those sparks can settle and they can start a fire 30 or 45 minutes later. So when you are welding, you need to have a space that is free of combustible materials, or you have to have a fire watch who stays for 30 to 45 minutes afterwards. So one of the elementary schools in town burned down some year from this. So they were welding as they were working on it, and then everybody went home, and then a fire started, an hour later from the welding spark started a fire and burned down the school that was under construction. So it happens a lot. Whenever you do this, you also, when you're wearing the welding mask, you can't see fire. It's not bright enough, and so if a fire starts, you need somebody who's not wearing a welding mask who's standing back to watch for fire, especially if there's combustible stuff around. You remember that place that they make the telescopes? I was there one time. I didn't know that they made telescopes there when I was there. I was there for marching band camp in high school, so yeah, us and the dinosaurs. It was awesome. But they were installing some boxes for people to be able to watch the football games. And so they had all these people up on this superstructure above the stadium. Well, somebody was welding this big superstructure together, and some sparks fell down into a barrel of solvent and started it on fire. All of the people who were on this superstructure, to get on and off the superstructure, the only way was in the basket that the skyscraper crane lifted up there. And so one of the people who was up there thought, well, this is bad because we're all on this structure and there's fire up here. So the best thing to do would be to kick this barrel so that it goes down onto the concrete benches below, and it'll just burn itself out and not damage anything, and it will save all these people who are up on the structure. And that was an excellent idea, except that they were welding, so when they kicked the barrel off, it landed amongst the gas tanks for all the welders that was right underneath it. So we were off on a totally different field, and there was this sudden boom, and this 55-gallon drum went flying up. There was fire coming out of it. It was pretty awesome. And it landed in the middle of the field. Pretty sweet. Anyway, but you should check your environment before you start welding, and don't weld above the barrel of solvent. Heat. You can't tell that stuff is hot till you grab it, so make sure you're wearing the right PPE. Stuff stays hot for a really long time after you've been welding on it. That seems like it ought to be obvious, but it is easy to have that happen. Radiation is a serious concern when you're doing this. It throws off a tremendous amount of ultraviolet radiation, and so you will get burns from it if you're not appropriately covered up. When I worked at Caterpillar, we installed 2 experimental engines on the island of Grenada down in the Caribbean, and that was really cool, but it was really sad because on the island they don't have many natural resources and they don't have much wealth at all. And so when you needed something like the cooling system that the company was, or the utility was responsible for installing, the only pipe flanges that they had were from ships that had come and visited and been robbed of all their pipe flanges because they were going to sink or they were, being taken out of service. So they just had these barges in the harbor that had a bunch of parts on them. And so the welders came up one day and we needed an 8-inch flange, and they were going from a 10-inch flange down to an 8-inch flange. And they did it all with weld. So they didn't have a reducer, they were just filling in weld. And the thing that was sad about it was the welders, the master welder was a kid, and I don't know how old he was. He looked like maybe he was 14. And his helper was probably 10. And so, and between the two of them, they had one welding mask, and the entirety of the rest of their PPE was they were wearing shorts and flip-flops. And they just sat there and welded for days to fill this weld in. But it was one of those things where, you know, they're gonna probably have skin cancer from doing that because there's so much ultraviolet thrown off, and there just wasn't, they didn't have any PPE and. Yeah. Well, yeah.
It's like stupid little sunburns around their welding masks from, I mean, not sunburns, welding burns, but.
Sure, yeah. Yeah, it would be bad. It would be painful. I don't know how they did it, but yeah, the helper just sat there like this, you know, trying to look the other way, and the welder was holding that, and it was sad. Anyway, noise, it throws off some amount of noise, and if you do it all the time, then you do need to have earplugs because it's at a level that will cause hearing damage. You have to be careful about what you're inhaling that's coming off of it, and so it's a good idea if you're welding in some enclosed space, you need to have plenty of fresh air coming in, and also just a way to vent air out of the space. Have to watch out for electrocution before you start welding. The easiest way is just to check your welding cables, make sure there aren't any cuts in them, and don't stand in the puddle of salt water while you weld, and make sure that the grounding clip is in good shape and that it is clipped to the thing that you're welding. Have to be concerned about pressure in the gases, the gas bottles. 8,000 PSI is no joke. It can cause serious damage really, really fast and do pretty cool things. We'll watch that here in a minute because it's just fun to watch. A lot of people don't wear safety glasses inside their welding helmet. Wearing a welding helmet, why would I need safety glasses? Well, after you've welded for a while, there will be a time that you're welding and a little spark will come dribbling down the inside of your mask, past your face and out the bottom of the mask. It always, you know, it will happen at some point, and so safety glasses even inside are a good idea. The other thing that people do is they weld for a while, they flip up their mask to look at it, and then they take out the grinder and do a little bit of grinding. So if you have your safety glasses on, then you're all prepared for the grinding as well, and you don't have to remember to put them on. So it's a lot safer. Have to be ready for explosions. So if you are welding a gas tank, you have to know how to weld a gas tank well. The fumes that are in there will cause lots of problems if you don't know how to deal with them. If you know how to deal with things, then you can do it well. So when I worked at Sandia Labs, we had two guys that I worked with who were master welders. One guy was just incredible, JJ, and he had lots of stories about welding things. Unfortunately, he had an uncle who owned a garbage truck, and they would often get called up to go weld the garbage truck back together, and he said there's nothing worse than welding in the back of a garbage truck where you're welding and there's stuff falling on you all the time you're welding. Really nasty. But JJ also talked about he got called when he was in his apprenticeship, he and the welder that he was working with got called out to a gas leak. So there been a backhoe was digging and it hit a metal gas line, and so they got called in to fix it. And so you know, they got there and the gas company was there, and he said, did you shut the gas line off? And they said, yeah, we did. And he said, okay, what I need you to do is I need you to crack that valve just a little bit so that there's a little bit of gas flowing out of it. And they're like, okay. So they crack the valve and there's a little gas flowing out of it, and what the welder does is he takes a big wad of newspaper, lights it on fire, and chucks it in the hole. And everybody's like, what the hell are you doing? And he knew that it was dangerous to weld on that pipe because they had shut it off. That meant that inside the pipe there was gas and air, so that could be an explosive combination. But by running the gas, it forced the air out of the pipe, and then it was just gas inside the pipe. Well, gas can't light on fire if it doesn't have the oxygen. So what they did was he threw the newspaper in there. It caused this little jet of flame to be coming out of the pipe. And then once that was happening, then they went down in there and they welded the hole closed while it had this little jet of flame coming out of it. And then when they finished, it just capped it off because the pressure wasn't that high to prevent them from welding. So if you know what you're doing, you can deal with explosives, but you have to be really careful with explosive environment. Yeah.
I was just gonna say that people weld gas tanks while there's gas in them, but that, your explanation made more sense.
Yeah, yes, though it seems wrong. I don't weld gas tanks. I would be willing to weld a new gas tank, but not a used gas tank. That's somebody else's. We have to watch for mechanical hazards. Stuff's sharp when you weld it. You have to watch for tripping and falling because you have this mask on that makes it so you can't see what's going on. And so tripping and falling happens easily over all this stuff. So we ought to watch this because this is just sweet for pressure safety.
High-pressure gas cylinders have been around for 100 years, and legends of their destructive potential have been around for 99. But could a ruptured tank really burrow through a brick wall?
It'll be back in a minute.
Into the next county.
Here we go, shearing the regulator off the tank. Attempt number 2. In 5, 4, cross your fingers, 3, 2, 1. That is a lovely, lovely sound.
The valve has sheared clean off, and that's a very good sign. It looks like the cylinder flew straight and true, but did it have enough thrust to crack the wall?
Oh, God. It was the lard that did it.
At 40 miles per hour, the air tank turned the cinder block to cinders. It even put a fair dent in the wall 6 feet behind it.
Totally. I mean, it didn't go all the way through, but it went through this one and it was gone. It's working its way through that one.
I was ready to see this as not possible. I was totally expecting it not to actually work because it's one of those impossible tales, and everyone we talked to had heard the story, but no one knew anybody that it happened to.
You know, this was an optimum situation for this tank. What this tank did is as good as it gets.
My favorite thing is the perfect roundness of the top of this hole. It also pushed this entire wall back a half an inch.
Although the cylinder was deliberately aimed, you couldn't ask for a more convincing result. So let's call this myth totally and spectacularly confirmed.
All right, there we go. Don't mess with 8,000 psi. All right, that's the end of today. On Thursday, some of you will be presenting. On Tuesday, some others of you will be presenting. In lab, we will be machining fidget spinners.
Wait, are we getting them today?
Yeah, see, but you weren't here to see the thing. Here, let's see the thing. There's the thing.
I see mine, I see it, I see it.